Okay, yeah, then thank you for the introduction, Alex. So as you said, I'm going to talk about ThreadSanitizer and how we utilize that in HPC correctness checking. So this talk goes a little bit into the direction of introducing ThreadSanitizer to those of you that are not familiar with that. And on the other hand, how we use ThreadSanitizer in HPC. So it's kind of a mixture of introductory course of how we use that, if you want to use that, and how we use that in our research. If you're interested to download the slides, you can use this QR code, because I've also added some links and references. So if you want to have a look afterwards, you can use it. But I have it also I can show it also later on. Okay. Then let's start. So I would like to start with a short example that you could come up regarding databases using different programming models. Here, for example, pthread example with the database. And let's just go quickly over that. So we're using pthreads here. We have a global variable. Then we create a pthread and say, yeah, this thread should execute this function thread1. And this function thread1 sets then my global to 42. And then we have the main thread, which continues execution and also sets my global to 43, which is in the end, of course, a data race between those two accesses here. And yeah, we all know probably or hopefully that this is undefined behavior in the end. I will have also other examples that you could think of if you have C++ threads. Yeah, then you could have something like that, a lambda that increments a counter. And then you have two threads that execute that, and then you have a database on this counter. And for those of you that are familiar with OpenMP, maybe you just raise your hand. Who of you has used OpenMP or knows OpenMP? Most of you. Okay, great. That's good. So here's just a simple example that you come up in a textbook, I think also. So we have OpenMP here with two arrays, and we want to compute the multiply the values and add it up to a sum. And then we use pragma OP para 4. Yeah, and the problem is we don't specify reduction clauses, something like that. This is also, of course, then a data race that we have here. Okay, so various programming models and data races. The question is, what do the standards tell us about data races? And they say, yeah, C++ standard, the execution of a program contains a data race if it contains two potentially concurrent conflicting actions, and at least one of which is not atomic and neither happens before the other. Any such race results in undefined behavior. Okay, so that the deciding point in the end is undefined behavior, because as you have undefined behavior, everything can happen in the end. Ranging from strange compiler reorderings that do funny things and so on. And then if you have a look at the OpenMP specification, it's basically the same. It says, multiple threads access the same memory unordered, at least one thread writes. If a data race occurs, then the result of the program is unspecified. Okay. What I said is undefined, unspecified behavior means there are no guarantees on what will happen at all. And what's really important is that, some developers sometimes talk about benign races. And there are no benign races. So each data race that you have in your code in C, C++, OpenMP, is harmful in the end, or can be harmful depending on the platform and things like that. I've also included a link if you want to read further on that, on data races. Okay, the question is, what can we do about that? So we have the data races. They are also often hidden. You have some counter that you access concurrently. They behave non-deterministically. That means, in one execution it works, in the other it doesn't. You change the platform, it's broken. That's something, that's hard to debug. And what you can use for that is ThreadSanitizer, which is dynamic data race detector that you can use for C, C++, also Go. And it works with LLVM, but it's also shipped with GCC. And it is mainly developed by Google, part of the Sanitizers project. So who of you has ever used a sanitizer of Google? Probably the ThreadSanitizer or something like that, or the ThreadSanitizer. So there are multiple such sanitizers that detect memory leaks or something like that. And there is one project called ThreadSanitizer that detects those data races. Yeah, there are different OS platforms supported, okay. And the typical slowdown that you can expect according to what is written in the paper and written in the manuals, kind of 5 times slowdown or to 15 times typical memory over 3 times to 10 times. But that depends on the program that you have. A little bit of history, because I think this is also interesting. The first version that was implemented of ThreadSanitizer based on Vagrant, that is this binary instrumentation framework, where we just run the binary and then instrument on the fly instructions in your execution. That was unfortunately pretty slow. And starting, I think, with version 2, yes, in 2012, it is part of LLVM, and they decided to change the design in the way that they do compiler instrumentation to instrument load and stores, then compile everything and then run it, because that's of course faster than instrumenting with this binary instrumentation. And then there was recently an update in 2021 on improvements of the memory overhead, shadow memory, and the vectorized race detection, but those are rather details. So important is that ThreadSanitizer now use compiler instrumentation. Okay, and how do you use it? Yeah, you basically compile your code with fsanitize thread, and then you run the application. That's it. Yeah, so you have, for example, Clang. You should turn on debugging symbols, of course. That's helpful. Take your code and run your application, and that's it. And if you do that for the example we had before, yeah, for the pthread example, here's again the code. Then you will get, when you run that, the following output. Yeah, ThreadSanitizer will tell you there was a data race, and it will also tell you that there was a write of size 4 by the main thread. Yeah, and also tells you where it was, where it is located. And the same is also true. There was a previous write of that one, and this write of this p thread that is created here. And you can basically attribute this information. Yeah, that means you can say, okay, this stack frame, not stack frame in the end, but this source location is located here. Yeah, where we assign that 43, and for the others, it's for the other access, it's located here. It also tells us that it's the global, and you can also see that where the thread was created. So a lot of data that helps you to identify the bug, because this is what you in the end need. Yeah, you need to understand where is the data race, and therefore you need source line information and information which thread created that race. Okay, so that's the simple example. And in this talk, I would like to shortly discuss a little bit the internals of how this is working. So how is this instrumentation working? How does this runtime analysis work? And then I would like to talk about an important tool that we use for HPC correctness checking in the end. That are those dynamic annotations, because they help us to additionally add information memory accesses into the ThreadSanitizer runtime, which helps us in the verification of OpenMP and MPI. I will also talk a little bit about that. So I would like then to conclude with some information on how we use ThreadSanitizer to indeed verify HPC applications. Okay, so let's start again with the internals. So I already talked about that. What do you need in order to detect database? You have to understand when the memory access takes place. Yeah, and for that you can use compiler instrumentation. And what is done with ThreadSanitizer is you take the LLVM IR and insert calls to the ThreadSanitizer runtime library. So here we have tsanwrite, tsanread, and then you pass the memory location. And it also inserts calls to function entry and exits to generate stack trace on detected traces. That means, if you enter a function, then ThreadSanitizer has an internal stack tracing implementation that also takes that information. So from a source code perspective, yeah, if you have this my global access, the following happens. Yeah, we first have tsan func entry and get this return address of this function. Then we say tsan write 4 because that's an integer, 4 bytes, and pass the address here of my global. And then when we leave the function, we call tsan func exit. Yeah, and if the race is then detected, ThreadSanitizer has all information it needs to detect that. For those of you that are familiar with LLVM, this is the copied, instrumented code for that. So it's basically, yeah, semantically equivalent, just another syntax. But this is how it's actually done in the LLVM. If you're asking now, how does GCC this? They also use something similar. I don't know about the internals, but in the end, they also add those calls in then on the source code instrumentation part. That means whether you use GCC or LLVM, doesn't matter. The runtime that is later on used is the same. Yeah, so GCC uses then the runtime of LLVM here. The other question is, okay, we understand memory accesses, that's great, but we also have to understand synchronization. And for example, pthread synchronization. When is the thread created? When is the pthread barrier called? And we also have to think about memory allocations to understand, I will later on talk about that shadow memory is used, we have to instrument that, or other synchronization constructs. For example, we have to think about C++ atomics that could lead to some synchronization. Most of those calls are just wrapping functions that are in the end called. That means tsan overrides then the pthread barrier, whatever symbols, and then provides its own and then passes it finally to the actual call. And for C++ atomics, there's also some, on the source level, some instrumentation going on. But most of the functions are actually wrapped by just saying I just have my modified symbol that is then called. Okay, great. So now we know we can capture memory accesses, we can capture synchronization. Now the question is, how is the actual race detection done? And for that, ThreadSanitizer uses shadow memory, which is an access history of the memory cells. That means you have for each memory location, stack, heap, whatever, a corresponding shadow state. And then you have 8 user bytes that are mapped to the same shadow state. And this shadow state itself consists of n shadow words. This is typically 4. That means you can, in one shadow state, you can carry up to 4 previous accesses in the end, but you can also increase that in order to avoid false negatives. Yeah, it could also be that you want to track more historic memory accesses, but this is configurable. And the nice thing about this shadow memory is that you can, if you have an access to a memory address, then you can look up the corresponding access history in the shadow memory by just adding an offset to that address, and then you know, okay, the mapping shadow memory cell is just something by adding something up to the current address, and this gives you kind of constant lookup times for that, and this is of course really important. You could also say I use a binary tree or interval trees are also something that are typically used for race detection, but then you have to traverse through the tree, and this is typically expensive, so therefore this is actually a good idea. But the other downside is of course the memory overhead that you introduce increases. And just for completeness, this shadow word consists of 32 bits in the end. So 4 bytes. So we have the access type where you say, okay, the offset, because we map 8 user bytes, we have to encode which of the user bytes are accessed. Then we have a thread ID slot where we encode the thread that accesses the memory. We have the epoch, which is a logical clock because tsan is a happens before race detector. I will talk about that on the next slide, how that is done, and then something if it's a read, if it's atomic, and so on. Okay. Yeah, the memory overhead totally, of course, depends on different things. Yeah, you have this, on the one hand, the shadow memory. This is somehow allocated when you have some allocation in the end or mapped into this shadow memory area. And you have, of course, stack tracing stuff that's going on. So this all you have to consider here. Okay. Just a few words about the actual race detection. So as I said, TSAN tracks the so-called happen before relation of memory accesses to check for concurrency. And it just says, yeah, if you have two events, for example, two memory accesses, A and B, and then you say A happens before B, yeah, in the program execution, then you know, okay, yeah, then you are safe. Yeah, because if you can guarantee that A happened before B, then you don't run into problems. If neither A happens before B nor B happens before A, then they are concurrent. And then if those are conflicting memory accesses, then you have a data race. The question is, of course, what influences this happen before relation? Yeah, of course, a barrier, a signal, weight. So if you have a barrier, then everything that was before the barrier happens before everything that was after the barrier and things like that. And you can track this happen before relation accurately with logical clocks, which is just a clock that you increment in the end for when you have a synchronization event or so, and have for n threads a clock with n entries that is managed at each thread. I'm not going into the details here, but in the end it's just counting the different events and then relating them to each other to understand, okay, is there a database or not? And in the end, what's done for the final race detection, there is a state machine that reacts to the different events, memory read, memory write, signal, wait, and things like that. And read and write will update the shadow cells and trigger data race checks, because for each write we have to check, is this in conflict with the previous accesses? This makes it, of course, also expensive in the end. This is why we have also the slowdown of 5 times to 10 to 15 times, depending on the application. And signal and wait, for example, update the vector clocks, because then processes wait for each other and things like that. Okay, this is the internal stuff, and I just want to give you a few examples on ThreadSanitizer options without going into all the details, because you can also look them up. If you want to, for example, avoid source code instrumentation, you have a function where you say, this is not of interest to me, then you can add an attribute and say, I want to disable the sanitizer instrumentation. You can also pass a blacklist to say, okay, don't want to have this function instrumented, I don't want to have that file instrumented in terms of memory accesses, because I know this is safe. Then there are also runtime options, but I'm not explaining all of them, so you can define suppressions and so on and so on. And if you want to have a look at all available options, you can also pass this option help here. So this is passed as environment variable just to the application when you execute that, and then it's automatically considered. And ThreadSanitizer can also detect other bugs, so deadlocks, leaked threads, and things like that, but I'm not going into the details here. What I would like to talk about is dynamic annotations. So now we have our ThreadSanitizer that can detect memory accesses and synchronization, but not all synchronization, and that's a problem. If you think about something like OpenMP, you write a pragma OMP parallel 4, and then some magic code is generated that ensures that there is parallelization and things like that. And this is problematic for ThreadSanitizer because it does not understand all the synchronization that's going on there. I will have an example on that on the next slide. Other things are, for example, non-instrumented shared objects, for example. You have, for example, a math library that you call, into MKL or whatever, or OpenBLAS, and this library is not instrumented, but it might do some memory accesses that might be in conflict with something that you are doing. And then the question is, can I somehow tell ThreadSanitizer that there is a memory access going on without instrumenting the whole library, which is also something that you don't want to do. And for that, TSAN provides a rather large list of so-called dynamic annotations. And those are calls that I can add to the source code as a user, or later on that also a tool can add. Like, okay, annotate, ignore reads, begin, end. You say the ThreadSanitizer, please start and end, ignoring any read access or write access or whatever. What's also important, if you want to annotate synchronization, then you have annotate happens before and after. We'll see later on how that works. And what's also important, if you want to annotate the memory access, then you have also something like teaser and read range, where you can say, yeah, I want to have this address with this size and want to have a memory read access on that's annotated. And there are many, many more calls or annotations that you can add. I've just put the link to those here if you want to have a look at them. And the point is, yeah, ThreadSanitizer cannot understand all synchronization, as I said, and this is also unfortunately true for some C++ features. So here in this code, yeah, we have two functions, write x before and write x after. And we also have an atomic flag that we set to false, and we initialize x with 0 as global variable in the end. Then we have our main function and have thread 1, which calls write x before, and thread 2, which calls write x after. And what we intend to do and what is indeed working here is that we don't want to have this excess here, yeah, x equals 42, and this printout here of x. We don't want to have a data race here, and therefore we have to somehow ensure that this x42 is written before this is printed out here. And in order to do that, we can use just poll here on this flag using a while loop. Yeah, we say while flag load standard memory order acquire is false. We just wait, and we wait until the thread here, yeah, this is done by the other thread, has stored true to the flag, yeah, so then we can continue and then print out the value. That means this is defined behavior. We will always print out x equals 42. And this is working with ThreadSanitizer. So ThreadSanitizer can understand the synchronization because it can see, yeah, on this atomic variable flag, there is something going on with these memory orders, release and acquire, so I understand that there is synchronization going on. Okay, here's now the same example, but we modified it a little bit. So what we did is we have now flag store memory order relaxed, and also here flag load memory order relaxed, but immediately afterwards we put an atomic thread fence with memory order acquire, which is equivalent here for this example to that code semantically in the end. And this is also true for the fence that we put here, memory order release before the flag store, because what we want to ensure is, of course, that this is not reordered, so the x equals 42. And the interesting thing is that ThreadSanitizer cannot understand fences. That means if you have a fence, yeah, it cannot understand. If you have an example like that, ThreadSanitizer will report a race, although this code is safe. And the reason for that is in the end, so I don't know about the internals, but here you can attribute the standard memory order released to a memory address, namely the flag. And here I can attribute load also to this flag. And here I just have a fence, which is not attributed to anything. And this makes it, yeah, I think from the implementation perspective, hard to understand. But what you can do, if you had such an example, okay, this is totally artificial example, but what you could do is you could say, yeah, okay, I know that there is synchronization going on using this flag. Then you can say annotate happens before. You pass here also file and line, but that doesn't matter. You pass here the address of the flag, and then ThreadSanitizer uses this identifier later on here with the annotate happens after to say, okay, there is synchronization going on. And with that, yeah, if you add that, the data race is correctly not detected, and you added here these two dynamic annotations. So from our perspective, this is a helpful feature because you always want to avoid actually false positives, and if you can annotate your own synchronization with that, this is actually pretty nice. Okay, let's go now to the HPC application use cases. So in HPC applications, often external math libraries are used. OpenBLAS, Intel MKL, I already said that. They are not instrumented typically by TSAN because they are shipped as a binary, so no instrumentation. It could nevertheless be that you have races between local memory accesses in your program, And the math libraries, if you do something, yeah, you have one thread that does something in the math library and another thread also something different, either in the math library or something like that. But this would be easy. I mean, if you know what kind of memory accesses this math function does, then you just annotate them and say t then write, t then read, whatever. This is easy. What is more complicated is if you have, I already talked about that, OpenMP as shared memory programming, MPI or remote memory accesses. So all these high-level parallel programming models that don't have just, like as for pthreads, you have just those calls, and in OpenMP you have those pragmas that you add. And this is more complicated. And yeah, as I said, Tison is not aware of this threading synchronization behavior of higher-level programming models. And therefore, we want to use the dynamic annotations to make Tison understand such synchronization. So here's an example, yeah, the example that we had before. We just have the sum that we write to, and we use pragma OMP-PAL4 without reduction. And Tison reports correctly erase here. Let's do now make that example working. So we have a reduction plus sum. There is no race in this code, but Tison still reports a data race. Yeah, and the reason for that is that it does not understand there is this internal reduction called from OpenMP, but this is something that ThreadSanitizer does not understand and says, okay, here's something going wrong, here's the data race. The same is true if, I mean, this is not a useful code, yeah? If you have a pragma OMP-PAL4 and you put in a pragma OMP-critical, that means that should be no problem. There's no race in this code, not that it would be performant, but ThreadSanitizer will still report a race on this code. And this is something that you don't want to have, yeah? So Tison does not know about that. And as I said, yeah, the solution to fix that is now to, for these three examples, so ways reported, the solution is to use dynamic annotations. Yeah, as I already said, synchronization constructs are implemented in libompso, an external library. And of course, Tison might intercept some synchronization if OpenMP, for example, uses internal P threads or something like that, but not everything. And there could be also synchronization using atomics. And the solution, actually, you have two solutions. Yeah, you could either say, I instrument the OpenMP library to some extent with ThreadSanitizer. This is tedious. You would have to build on your own, and I have to admit I did not do that so far on my own. Or what you can do is you annotate OpenMP synchronization with dynamic annotations. The question is, how do we do that? And the answer is, OpenMP comes with a nice OpenMP tools interface that's called OMPT. And this gives you callbacks that you can use. Yeah, those callbacks are invoked by the OpenMP library. And then you can say, when a reduction is triggered, then you get this information. Okay, there's a reduction started, and you can hook into that and can then use this callback and can then add annotations. Yeah, and for example, yeah, here's also the critical region example. When you enter a critical region, then you get the callbacks, OMPT callback mutex acquired and released. And this is pretty helpful because we can just map the callbacks that we have, mutex acquired and released, to dynamic annotations. That means in our tool, we just use dynamic annotations, and then we are fine. And this is what our tool Archer does, that has been mainly developed by my colleague Joachim from Aachen, in collaboration with Lawrence Livermore in the US. And it's basically an OpenMP extension for Tison, and it does what I've just described. You take the OpenMP events and map them to annotate the synchronization. Yeah, if you have a critical region or barrier, just use annotate happens before or after. For the OpenMP reduction, this the annotate Tison ignore writes begin end is used because within the reduction the assumption is OpenMP does the reduction right. Yeah, so therefore this is used here, and it also supports OpenMP tasking, task dependencies if you know about that. So can annotate all like that. And this is already upstreamed in LLVM, and if you now take Clang and just use fsanitize thread, it will be by default activated. That means you have to I explicitly disabled it for the examples that we had before. So when you run with OpenMP, you don't have to do anything. You just have fsanitize thread, run it, and it just works. If you want to read more about that, then you can have a look at this OpenPT teaser CPP in LLVM, which basically, maps these OpenPT events to the annotations. And there's also, if you want to read on that, a paper on that. Okay, that is the OpenMP example. The other example is regarding MPI. And my first question is, who of you has used MPIs before? Oh, nearly everyone. Okay, great. But just to give a short introduction again how that works. So MPI is the message passing interface, commonly used in HPC applications. And the idea is that you can send messages between processes in a distributed memory system, so HPC cluster, but also on a normal computer, of course. And what you do is, you first initialize the MPI library, and then you say, what is my own rank? So each process, if you execute the code with 2 processes, then each process will get an identifier. And then you can use here this branching and say, if I'm process 0, I will execute this here, and if I'm process 1, I will execute that here. And this is just a simple example where we send some value 42, using MPI int to process 1, and we receive that and then print out rank 1 received value from rank 0. That is so far no problem. You have in MPI also those non-blocking operations that you should also be familiar with, and those calls immediately return without completion. That means you have explicit calls to MPI wait. So here we have the usual send, and here we have the non-blocking equivalent. And we have to use this request object here that we will wait later on. Then we set our value, and then we say, please transmit this, but this will immediately return. That means here this value does not necessarily have been read at when you return. And only after you call the MPI wait, you can be safe, that this value has been read, and therefore there's no problem. But if you do something like that here, that means you say you have your MPI send. I sent value 42, but then I set value to 1337 before I call the MPI wait. Then you have something like undefined results, because it's not clear if 42 will be sent or 1337. In the end, you have something like a data race, because the MPI library might run in a thread or asynchronously copy something. And this is something that you might want to detect, because that's also a typical problem or misunderstanding, that you maybe don't understand that this value has not been copied to a safe place when you return from MPI send, but only after the MPI wait terminates, returns. Yes, and the question is, how can we detect such a situation? I mean, we don't have any threading here. We have a program that is just single-threaded that executes that. And for that, we have another feature that's also helpful for that situation. That's called fiber. And the fiber is something that can represent thread local concurrency in Tison. That means although you are single-threaded, you can say, I have a region which is concurrent to the execution that I'm currently running. And this is called a fiber. I will have examples on that on the next slides. And the nice thing is that you can create such additional execution contexts that are concurrently going on at runtime. And for that, you again have annotations, of course. So you can say, I want to create a fiber, I want to destroy a fiber, I want to switch to a fiber, the execution, and so on. And the question is, of course, now, if we have those dynamic annotations, how can we use them? And this is actually written here or depicted here on the right. So we have our value equals 42. Then we have our MPI send. And we somehow have to now tell ThreadSanitizer, there is a read of this MPI send going on between the MPI send and the MPI wait. And in between, we have this value equals 1337, which leads to a database. And this is in the end, yeah, the idea we somehow have to tell ThreadSanitizer that this here is going on. And in this red region, yeah, we should not modify the value here that is used in the MPI send function, because here in this region, the value could be red. And this is basically written here. So we create a fiber for each non-blocking operation, and the concurrent region starts MPI send and MPI wait. And this conflicting access would then lead to a waste report. Okay, great. I would also like to shortly show you how that works in practice, just if you want to recapitulate that later on. So what we have to do, yeah, if we have our, okay, my pointer is not working anymore for some reason. Okay, now it seems to be working again. We have our MPI send, and we first have to say, yeah, okay, we have an ISEND and we have to create a new fiber and get also our current fiber. So there's also always the default main fiber. We create an MPI fiber or MPI send fiber, and we switch to that fiber with synchronization. That means this is what you can see here on the right with this fiber switch. So we, of course, want to have all previous memory accesses. They happened before that, yeah. So value 42 should not be in conflict with the MPI ISEND. So we say we want to have an happened before relation here between the fiber and the main fiber, the MPI ISEND fiber and the main fiber. And then we annotate the read access of the MPI function. So we call tsan read range. And then it's somehow reflected here that you read that value. And then we have to already write a synchronization point where we say, okay, at some point later on, the ISEND is also finished. So we have to use an annotate happens before at that point, but this is established later on. And then we switch back, yeah, from the MPI ISEND fiber, and then continue with the usual execution. So value equals 1337. Yeah, and this will then lead, of course, to erase because there is no happened before relation between the read and the value. And what is important is, of course, yeah, in the end, yeah, when we have called the MPI wait, we have to ensure that everything that happens after the wait is not in conflict. Yeah, that means everything that is after the MPI wait does not lead to erase, and therefore we have this annotate happens after. Yeah, right. Okay, so just implementation details. And if you execute that with ThreadSanitizer, yeah, you have this example here again, and you have those annotations, of course, in between. Then you will see that you have here the data race that is detected by ThreadSanitizer, and it tells you, yeah, there is the ways here in the access here in line 5, and we have here the MPI ISEND, the value access. Yeah, so actually a pretty nice feature to also, although we are single-threaded, detect such races. Okay, great. The point is, of course, yeah, you don't want to do that what I did manually in your code, of course, yeah. So annotating this manually is not feasible in practice. And the question is, yeah, can you do that automatically? Is there a tool that can do that? And for that, we have a must, which we develop in Aachen, which is an MPI one-time correctness checking tool that can detect deadlocks, type mismatches in your MPI programming, leaking, MPI handlers, and data races involving function calls. And what it does is it intercepts functions at runtime to track the status of MPI operations. And must internally then now utilizes TSAN fibers to annotate all those memory accesses that we've seen before of MPI ISEND and so on. And those races are then reported by TSAN, and must can also collect them and format them in a nice HTML report. If you want to take a look at it, I've also included the link. So we actively maintain this tool must, and it's also open source. So if you're interested, you can just try it out. Okay, so those were the two examples. So we had OpenMP reductions and things like that with this Archer tool, MPI, this thread local concurrency. Question is, can we do anything else, or what can we do with the fibers? Another use case for fibers is OpenMP tasking. So if you imagine such a code here, yeah, you have pragma omp parallel, pragma omp single creator task pattern, and you have pragma omp task of and access x, set x to 42 and x to 1337. Then this is a data race. But the problem is, this is only detected as data race by ThreadSanitizer if those two tasks are executed by different threads. Because ThreadSanitizer says, yeah, if you have two memory access from the same thread, that's not a problem. That means, depending on how your runtime system is implemented, or you just pass omp num threads equals 1, it will not detect a race, although there is a race in that code. And the question is, couldn't we work with fibers in that example? And the answer is yes, we can. And this was also one of the original purposes to add those fibers. Each task is just spawned as a new fiber in the end. That means you know, okay, there is a fiber for that task, and you annotate. You have those accesses in that fiber. And therefore, you can even, although this data race does not occur in execution because you have only one thread or that executes the test, you can still detect that. And this is, I think, also a helpful application of those fibers here. Yeah, so as I said, yeah, that's written on the slides. Each task is modeled as fiber, so races can be executed even if all tasks are executed by the same thread. So actually also a nice example. There's also prototype integration in Archer. This is currently not integrated in Archer, but is planned to be added and called then task-centric analysis. If you want to further read on that, I just, again, included the link. Then the last use case I would like to talk about, because that's what I'm researching on, is RMA races. So those of you that know MPI maybe also know MPI RMA. In MPI RMA, you have processes that can remotely access the memory of other processes. That means you have process 0 here that can just directly read the memory of other processes, although they do not share memory. And the nice thing is that the target process is not involved in that communication as you would have it for MPI send, MPI receive. So you have some kind of shared memory semantics in a distributed memory environment. The question is, if you concurrently modify here something, yeah, with a local memory access, yeah, then you have the problem, yeah, you have here remote write from this process and the local memory access. And this is not supported by ThreadSanitizer, yeah, because ThreadSanitizer only works on shared memory programs. It cannot capture this distributed memory space that you have here. And the other problem is that memory consistency in such models is way more complicated. And what we did again is we modeled these accesses from remote processes as additional fibers, yeah, that we added here in order to detect those situations, yeah. And then even in this remote memory access scenario, you can use those fibers to say, yeah, okay, there's something from remote going on that's concurrently. And again, such a nice use case for that. And that's the tool is called Must RMA. It's part of Must in the end. And again, we use Must and TSAN, so Must was our MPI correctness checker, to detect those regions and annotate them. Okay, with that, I would like to sum up or wrap up what we've seen. So we had a look at ThreadSanitizer database detector for shared memory programs, which instruments memory accesses and dynamically instruments the synchronization calls, supports P threads and C++ threads, and uses happened before relation to understand the concurrency of events. Typical slowdown is between 5 times to 15 times. Memory overhead ranges from 2 times or 3 times to 10 times. And we had a look at dynamic annotations, that enable the support of other synchronization mechanisms like OpenMP with Archer, fibers with the MPI non-blocking operations, OpenMP tasking, and RMA models. So this is it. I would like to thank you for your attention. Hope you learned a little bit about how we use ThreadSanitizer and how you can maybe use it. Okay. Any questions? Yes. Um, Yeah, you could, yeah, there's efforts in that direction, of course, but I'm not aware that running ThreadSanitizer natively on the GPU is something that is currently pursued. But we also thought about doing something like that because, I mean, on the GPU it's basically the same, but of course you could also say I executed on the host parts of it and try that. That is a possibility. But I don't know if there are any efforts ongoing on that direction. What you can of course do is, uh, um, for example, if you have Fagma OMP target stuff, those mappings, this is something that a colleague also thought about, that you have um, databases where you have a target data map and modify the data while it is copied to the GPU or something like that. And the other thing is that something that we are pursuing here with Alex together is that you have, for example, a CUDA-aware MPI, where you say I have a non-blocking MPI send, and you would then also concurrently copy something to the GPU. But this is again ways between then the host access, the MPI access of the GPU memory and this copy, but not on the GPU itself. Yeah. So this is something. Yeah, I think it's just yeah, probably way more expensive on the GPU to have this shadow memory. I mean, memory is at least was a more limited resource than on the host. I mean, that has changed to some extent, of course. Yeah, but again, I don't know if there's anything ongoing. I only know of static approaches that try to detect races and others that then use simulators to detect races on CUDA kernels and things like that. But again, nothing that is clearly regarding yeah, dynamic, so executing and checking for ways. Yeah. No other questions? Yeah. Okay. No. Yeah. To be honest, I'm neither a SQL expert nor a Cocos expert, so I don't know, to be honest. But I think that would be also an interesting direction to check whether there is something on non-blocking in the end ongoing, what you could annotate. Yeah. Yeah, okay. Yeah, if you have a backend for OpenMP, then you could of course say, yeah, I just detected then on the OpenMP level. Yeah. Mm. Yeah, right, right. Yeah, yeah, definitely.
Usually take some slowdown in account when you do correctness checking, but yeah, having thousands of threads call your fiber create callback only to pass through back to your CPU.
Yeah, definitely.
Like fun time to do this.
Yeah.
Synchronization depends, like full if, on the value of variable that gets set by another thread.
Yeah.
Certain execution patterns.
Right. So in the end, it's a dynamic. So the answer is no. So it does not construct or have a look at different execution paths that could also be triggered. This is something that you have to do on your own. So if you're unlucky and the data race is not observable in some kind of way, then you have a problem. Yeah. So the question is always what is observable, but in the end, if you have an execution path where the database does not occur, since I mean, a typical example what happened before, where you had run into false negatives is where you do not detect the race is if you have a locking order where it's the locking is on the first execution like that the race is not triggered because you have the synchronization in the right order, and then you don't detect that. Yeah, so it's a disadvantage of those happens before race detectors because they only see the execution. There are also log-based approaches that use just log sets, but that does also not make sense in most of the execution. That leads to lots of false positives. So it's just a trade-off. So it happens before race detectors typically have false negatives, as you said in such scenarios. But yeah, this is something that you to some extent have to live with. Of course, there are approaches for MPI. I know approaches that try to understand all the execution paths that could occur. But this is something different. So I don't know if there's something for other synchronization pattern stuff. So it does not do that automatically. Short answer. Okay. Okay, great. Thank you.